In the last lecture, we looked at the loss surfaces for the constant model using both average squared loss and average absolute loss. Those looked like this. So in the top right, we have the average squared loss or mean squared error for the constant model for our given data set. And so you can see the x-axis corresponded to our choice of theta, which there was just a single scalar. And on the y-axis, we had the mean squared error for that choice of theta. So, if we pick theta to be 35, the mean squared error would be, something near 150. And so this clearly tells us that theta being 25 was the, choice that minimized mean squared error. On the bottom, we have an equivalent plot, but when we were using absolute loss as our loss function, so our plot was of mean absolute error. And this sort of told us that theta being 22 here minimizes, mean absolute error. But now for our simple linear regression model, we don't just have a single parameter, theta. We have two parameters, a and b, or, if we're reverting to the more traditional notation, theta naught and theta 1. And so our loss surface will be 3D. And this is what that looks like. So we have one axis for theta naught, or a, another axis for theta 1, or b, and the height of this curve tells us the mean squared error for that combination of parameters. The yellow point that we have down here occurs at the minimum value of the mean squared error, which corresponds to the optimal coefficients that we just solved for. So let's take a look at a demo of this. And again, you can play around with this on your own. I've created two helper functions for us, one that will take in a list of y values or true observations and a list of predicted observations y hat and give us the mean squared error for those predictions. And I've created another function that will take in my a and b as a list. I use t for theta here. So it takes in my model parameters as a list and returns the mean squared error for that choice of model parameters for our model that is using a child's parent's height to predict their height. Now this gigantic ugly block of code, what it's doing is it's plotting the value of the mean squared error for several different values of theta. And so we will, be replicating this nice curve that we saw in the slides. And what it's also doing is placing a nice big point at the optimal parameters a hat and b hat that we solved for, a couple videos ago. But anyways, the result is pretty nice. And so you can see we have one axis for theta 0, or theta naught, I should say, one axis for theta 1, and the height of this curve tells us the mean squared error. What's cool with Plotly is I can, look at this curve from below, and if I put my mouse on top of the gold scatter point here, it sort of tells me that the value of theta naught that I'm looking at here is, 26 point something roughly. The value of theta 1 that I'm looking at here is 0.61 roughly, and the mean squared error for that choice of theta naught and theta 1 is 5.32. If I move my mouse anywhere else, you can see that the mean squared error is higher, right? Even if I move it, a little, the mean squared error is higher. So the gold scatter point that I have here truly is the minimum. And if you look at it from several different angles, you can see that it's the minimum. I encourage you to play around with this because it is pretty cool. But this is an idea of what a loss surface looks like when we have multiple model parameters. You may note that this does look very smooth and parabolic-like, which is one of the properties of squared loss that we discussed in the last video. Now, this is not the last time that you will see loss surfaces that look like this. When we start talking about numerical optimization procedures like gradient descent, we will be, looking at plots that look like this quite frequently, but we will cross that bridge when we get there. So that's a loss surface.